Welcome to the Math Record. Today we'll be covering the one-sample t-test and its confidence interval. This video will cover Chapter 2 of Part 1 of our statistics class. Okay, let's get started. A one-sample t-test. A t-test as compared to a z-test is that a t-test uses means, as I said in like some videos before, that it uses means or averages, except in rather than using proportions that z-test is used. So if you ever see any numbers just by itself and it's using like averages from a bunch of other numbers, like they combine a bunch of numbers and find the average, then basically you're going to use a t-test. The difference between a t-test and a z-test is that a t-test, so a z-test will look something like this, right, where it's symmetric. A t-test will also be symmetric, but it's got to be more flattened out. It's got to be something like this, right? And it's gonna have a bigger spread. So if this one is this first standard deviation, right here would be a standard deviation for t. So have a higher spread, basically. And that's basically the gist for a one-sample t-test. A one-sample t-test is when you are getting one sample and you want to use that sample to like determine basically a claim. And because there are multiple t-tests and there's a one sample, a two sample, and a paired. For a one sample t-test, it's just when it's basically getting one sample and you're trying to like dispute or like approve a claim that they're gonna show later. I'll show this in later on in the example in the end of this video. As always, when you're using a one sample any single test, a z-test, a t-test, or a chi-square test, you always have to check conditions first to see if you could use it. Okay. And always, as I always said before, always you use random, which is saying that the sample is random. So any data in the sample that you collect, like if you collect people for your sample, the data is so you randomly selected those people. You can't like just go up to like your friends and family and just like ask for a sample. So like that example basically. So you have to have like a sample that's random. Next up, you have to have independence, which basically, as said before in my z-tests, individuals are independent of each other. So IND, I'll say that's individual is IND is independent of each other. Because you can't have, just because you chose one thing doesn't mean the next thing to be chosen it has like a higher or lower probability. So like if you flip a coin, you can't, just because you get a head the first time doesn't mean you're guaranteed a tails on the second time, because they both have a 50-50 chance. You know, it doesn't make sense. So you can't so it has to have independence. So the probability stays the same. Okay? And now you have 10% condition, which is that your sample size, which is usually in variable n, which refers to your sample size, has to be less than 10% of the population that your population that you're observing. So if you're studying like high school students, that n has to be less than 10%. The n of your sample size has to be less than 10% of the high school students that you're observing. Like basically, if you take like 10 students from your high school, then those 10 there must be more than 100 students in your high school, basically, as your population. Sorry, I don't know why I deleted that. Population. And then the last thing you have to check is not while the z-tests are the ones that you test for sample size. For so one sample t-tests, the ones you have to check for is a nearly normal condition. This basically means that if you're given a bunch of data and you make a histogram out of it, like basically if you make a histogram, right? something like this or something, right? The histogram has to be approximately unimodal. Has to be unimodal. So it only has one peak. Right here has like two peaks, but you can see that's kind of like similar right here to here. So basically, you could say it's approximately unimodal, so it's fine. And it has to be symmetric. So you can say it's approximately symmetric because this side kind of looks similar to this side. So you can say it's approximately symmetric. Um, if you are not given a histogram, like if they just give you a sample size, you could bypass it having to say having to check if it's unimodal or symmetric. If your sample size n is, I usually use a number around like 40. So if it's 40 or more, you could use 30 or more, but I usually just stick with 40. 40 is good for me. It's, you could change the numbers, but it's kind of debatable. That's fine. 40 is not the actual number. I just use that number. So if it's 40 or more as your sample size, you have sample size of 40 or more, then basically you could just say your histogram is nearly normal, basically. So when you have to write this, when you write your conditions out for this, for the nearly normal condition, you have to make your histogram if you need to, or if you have n. If you have n, just write the statement that I'm gonna do right now. Or if you have the nearly normal condition, you basically you have the data, you put the data in, and then you see if it's symmetric and you approximately symmetric or and unimodal, and you just basically do that. Whenever you do this, you always have to make a picture. So you always need a picture. I'll just write pic. So you always need a picture. You need to draw it out, and then you have to say your histogram is approximately or nearly. You could use one of those words, approximately or nearly normal. That's basically all you have to write. So nearly normal condition. Okay. And now, after you basically check all your conditions and all of them are met, and you draw your picture for your histogram and everything, or if you only have data, you don't really have to draw it because you can't. Then basically, you write your transition statement. Every single time you do a test, any kind of test, you always make a transition statement. So you have to write, since the conditions are met, I can construct a one sample t-test. Basically, your transition statement overall for just any test is that you always write, since the conditions are met, I can construct a, and then whatever test you're going to do. So if you're doing a one port z test, just say I construct a one port z test. Or like you do a two port z test, I say construct a two port z test. So basically, you could just keep this statement overall the same, and then you just basically change this section all the time and get the right the test that you want to do. You just have to determine which one because they have different tests. If it's symmetric, just use and it's a proportion, use z tests. If you see just any other number that's not a proportion, it's probably just going to be a mean or average. So you're going to use a t-test. And anything that's skewed where you're comparing distribution with charts, basically you use a chi-square test. And after the transition statement, you do the test. Basically, you always follow that order, which is condition, transition, test. Then you define your variables. Then you do the math, and you make a picture and stuff, and you write your conclusion. And if you want to follow up with a confidence interval, basically. Now we're gonna go on test, which basically your null hypothesis (HO) is gonna be that for instead of writing P, which is what we use for z tests, which stands for proportions, we're now going to use something like U. So basically, U it's kind of like a U, and it's gonna be, and this stands for mean, right? So now your new mean or average is equal to the mean O, which is basically means subscript 0, which basically means that the mean that the true mean is that it's equal to the mean that they claimed. So if a company claimed that 20% of uh um on average that 20% is I mean not 20%, on average 20 of their products is like some kind of is like red on average, then basically since 20 is a number and not proportion, then basically you could use it as a mean. So you write U. I'm not exactly sure what the correct term is, but I usually just write it as a U. And then you have the alternative hypothesis, so HA, A for alternative. It's U is either greater than the one that they claimed, or the actual mean is less than the mean that they claimed. It kind of looks like a W, but it's just like a U and then like a little smaller one, kind of. Or U is not equal to the one that they claimed. Because whatever the variable stands for, I bet it's the true mean, not the one that's claimed. So you're gonna have a true mean. So the U is gonna be your true mean, the true one, the real one, but you don't really know what the number is, which you can't really calculate. And then you have the one that's claimed by whatever you think is true, and then you're gonna have your own U, your own mean, which I'm just gonna call as mean. It's gonna be your one from the sample. So those are the three types. So you gotta use your sample and compare it to your claimed and see if it's kind of true. So you just gotta do comparisons basically always with tests. So basically there are these three types. So you just have to logically think about the question whenever they ask you. So you have to only choose one of the three, only one of these three. So if they ever ask like, do you think they're like underestimating the mean? Then basically you gotta say the true mean is bigger in it, because if they're underestimating it, that means then you logically think the true mean is bigger than it. Or if they're saying they're overestimating it, then you have to put the true mean is less than it because they're overestimating. Now, if you say, do you think it's any different from the true mean, then you just have not equal to, so it's different. So you just have to logically think which one is true, and you just have to use the right one. Okay, so that's basically for the tests. And now you define your variables. So define variables. As always, you don't always have to do this, but it's good to have just so you keep track of what you're using. So the mean, the no mean, is the one that they claimed. So mean, average, or mean or average doesn't matter, which is claimed to basically be true. And you have the one that y is how we usually represent our mean. Is what we call mean average of our sample. But usually this could just be written as mean. You really don't have to write y, but y is a good symbol if you don't want to write as much. And then you have n, which always means sample size. You always have to put this in context, though, so you can't say a mean average claimed. Okay, now let's go on to the mechanics, which is basically the math portion. You probably could skip this step, which I'll show later on in the video, where you could just use your calculator and you could just write down all the numbers, but I'll just show you how to actually do the math. So you have your mean for your mechanics, which is equal to your mean your no mean, which is what they claim to be true. And then you have your standard error, which is equal to your standard deviation, whatever you find for your standard deviation of your number. So they usually either give you this as a question, if you're getting a question, they give you the standard deviation, or if you ever have a table, then basically you just find the standard deviation of that table. And then you have that standard deviation divided by the square root of your sample size. Right? And then you have your t-score. So you have z-score for proportions because of a z-test, and now you have a t-score for mechanics. So t-score is equal to your sample, which is your y, which is basically your mean, minus your UO, basically the one, whatever you, just the mean of your sample minus the mean that they claimed, divided by the standard error. And for t-tests, there's actually a family of t-tests, so it kind of works differently if you have different sample size. So there's something called degrees of freedom. So basically, how free is like basically the t-score is. So how like spread out basically. So what it really does is that if you have a lower sample size, it kind of has this really big spread. So what you have to do is that basically you don't really have to do the math on this. Well, what you do is that you plug in your calculator and they'll give you the answer. Usually, what I do, you don't have to write the entire degrees of freedom. I usually write lowercase d and then uppercase f, so it says degrees of freedom. And whatever the degrees of freedom is equal to whatever your sample size is minus 1, basically. And then you always have to write your alpha level. Your alpha level is usually 0.05, so just write 0.05. And then always when you're doing the mechanics, just draw a picture and label. So you have like something like this as your T. So it's a little bit more flattened out. It doesn't look like a Z test. But if it looks like a normal model, it should be fine. It doesn't matter either way. And then you have mean, so you write UO, and your standard error, whatever your standard error, right on top. And then basically just whatever your Y is, like let's say your Y is like right here, and basically just find your area. And then you should be fine. Okay? So always draw a picture with the mechanics. And next up, and then you basically use your calculator, and to calculate the p-value, you basically just plug everything in. Because like how, except for like the z-test is where you plug it into normal CDF in your calculator. Now for this one, you plug it into your basically your CDF. And then after this, when you get all your numbers, you write your conclusion. It's basically the same thing as the z-test. So it's based on your p-value. So if your p-value is less than 0.5, your alpha level, then basically I reject the null hypothesis. I would just HO, right? The null hypothesis. And you say there is evidence to suggest the alternative hypothesis is true. Okay? But you always have to put this in context. So I'll show later on in the example, basically. So you write based on my p-value of whatever your p-value is, which is less than the alpha level of 0.05. So specify is the alpha level of 0.05, or if whatever alpha level that you want to use, which is like if you want to use the alpha level of 0.1, then I say I reject the null hypothesis. There is evidence to suggest the alternative hypothesis is true. So that's what happens if the p-value is less than 0.5. Now, if your p-value is greater than 0.5, you say I fail to reject the null hypothesis. And then you write there lack evidence to suggest um, the alternative hypothesis is true. And you basically write this in context also. So you say so you write down in words based on the p-value of whatever p-value is, which is greater than my alpha level of 0.05, I fail to reject the null hypothesis. There lack evidence to suggest the alternative hypothesis is true. And you have to put everything in context. So talk about what is your null hypothesis. Talk about what. So you talk about what is your null hypothesis. So you put a comma and put like null hypothesis, and you say there lack evidence to suggest the alternative hypothesis. And you put context for alternative. So you put a comma and just write your alternative hypothesis is true, basically. So you always do that. And once you do your test, if they ever ask you to follow it up with a confidence interval, So you want to find like what is the true like where the true mean is located. Well, it's gonna be in a range. So the confidence interval. So your mean is gonna be at your y. So your sample mean basically, and your standard error is as your sample standard deviation divided by square root n. So basically the same idea. And then you basically have to find the numbers, the intervals is a mean. So it's basically your y plus or minus your t-score. So whatever area you want to find. But finding your degrees of freedom of n minus 1. So if you want a 95 area and you have a sample size of 100, you have to find the inverse area of 95 to get the t-score. Degrees of freedom of basically n minus 1, so you have 100 as your sample size, so 100 minus 1 is 99, so degrees of freedom of 99 times, so you multiply that t-score by the standard error, and you basically get your two numbers. And then you basically write I'm something percent confident the true mean value, not the proportion, because for proportion for z-tests, and for t-tests is means and averages. So you say I'm like, let's say you're 95% confident. I'm 95% confident that the true mean value of whatever you're talking about, write it in context, is within the interval, and then you write your interval using this number. So you have the lower interval is the -1 and the -1, right? And then the upper interval is the +1. So you have to do both of the math for this. Okay. So this table, okay. So for example, throughout the year, a student took hundreds of tests, okay, and then this table only shows like 40 of those tests that's chosen randomly. So these are 40 of his scores, okay. So the question is, to pass the class, he needs to score an 80 or above. Is the student likely to pass? Okay. So basically, the first thing you need to do is that if I'm using Nspire, so basically you go to your Nspire and you go to your down to your spreadsheets, and you have your spreadsheet. You gotta put this all into one column basically. So what you're gonna do is that just click the for A, like column A. You can name it whatever you want. I'm just gonna name it X. Usually you just need to name it X. You don't have to put it that. You don't have to be very specific. Um, And then you basically put all those numbers down. So you put 150, 155, a 50, a 55, a 60, four 365s, 166, 167, 370s, 271s, 172, 370, 474s, 73s, 274s, 475s, 376s, 177, 179, 280s, 181, 183, 485s, 190, 195, and 100. Okay. So based on this, just press on in your calculator and it should get you back to your menu, basically your original menu of your calculator. And then go to the one right next to it, which is called Data and Statistics, the purple one. And you click on it. And then if you look at your upper left, the 1.1 is your spreadsheet, so you could just like use your mouse and you kind of just like move over it if you want to see your spreadsheet again, or you could just and then you click the 1.2 to get to your to basically your graph. Now go all the way to the bottom and click the bottom. Click to the add variable, not the left one that says click to the add variable, the bottom one. Then click on that one and you click your variable x or whatever you name your column as, basically. And then you get this dot plot, and then you go to plot type, and then go to menu, go to plot type, which is number 1, and go to histogram, which is number 3, and then you basically make a histogram. So this histogram is kind of looks something like this. Then you have something right here. You have something up here. here, 2 down here, and then basically 3 more. Okay. So for this histogram, to satisfy one of the conditions for the nearly normal condition. So this thing is unimodal right here. And then even if it wasn't unimodal, if it's something like this, right? And there's like 2 peaks, you could say it's approximately unimodal because like this difference here is not that much of a difference. So you could say it's approximately unimodal. But it's good to know that it's actually unimodal. And then you have to find out that if it's symmetric. So this side over here looks kind of like this side over here. So you could say it's approximately symmetric, so it's fine. So this satisfies the nearly normal condition. So basically, you could just say that the histogram is approximately normal, and you just need to write that down. So you have to do that's one of your conditions. Okay, let's do the rest of these conditions. So uh, uh conditions. So you have random. So the sample has to be is randomly selected. So you could basically write down that the 40 test scores are randomly selected in the sample. Sample is randomly selected. Selected. Or you could just say the sample is randomly selected. That's fine too. And then independence. Just because you like score like a 40 in an 80 in like one test doesn't mean you're guaranteed like another 80 in another test, basically. That's what it's saying. So test scores are independent of each other. Are independent. Okay. And we need to do the other ones by running out of space. The 10% condition. So your 40 test scores, your sample size, is less than 10% of all the test scores you took. Because you took over hundreds of tests, but so 40 is probably less than 10%. And then we have the nearly normal condition, which we already did. Nearly normal, which basically condition, which you have to draw your picture, as like I shown before I deleted it, in the like few minutes past or seconds, and then you talk about like if it's unimodal or symmetric. If you don't have any of the data, like the chart that I gave, basically you just say if n is greater than 40, as I said before. If it's greater than 40, or if it's 40 or more, or if you say 30 or more, it doesn't matter. You could say that it's approximately normal just because of the sample size. Okay, just remember to draw the picture. So so you have your conditions met basically. Once you met your conditions, write your transition statement. I'm not gonna write it now. I'm just gonna say it. Basically, since your conditions are met, I can construct a a one sample t-test because it's basically one sample, and it's not a proportion because you're working with actual means. You're taking the mean of your tests, and you need a score of 80 or above to do it, which none of them are basically proportions. Okay, let's now work with the test. So your HO is that your actual mean, like your test mean, is equal to 80 because that's the score. You always have to write it. So your UO is 80, and your H alternative hypothesis is the U, the mean. It's greater than 80 because you need 80 or more to pass the class. So it has to be greater than 80. Okay, and now you basically just define your variables. So your UO is equal to the mean average past the class. Basically, put everything in context. Class. Okay. And then we have y, which is the mean average of your sample of your sample of your test scores. Basically, mean average test score of your sample, and then n is your sample of 40 tests. Basically. So write everything in context and you should be fine. Define your variables, and now let's actually do the math. So this is the mechanics. So you're gonna be using a calculator for this basically. So I already put what you know. You have the mean, which is equal to your HO, your UO, your mean, your original mean, which is 80, because that's the one that you need to reach. And then you have a standard error. Your standard error is your standard deviation. You're gonna use your calculator for this. So your standard deviation, go back to your spreadsheet, which is 1.1. So just scroll up to the 1.1 and click it. And then on like one of the basically the rows or columns, doesn't matter. Just don't be on like the blue part of your Inspire. So be on like the white part. And then click menu, click data, and then go down to number 6, which is list math, and then click your sample standard deviation, which is number 7. And then you're gonna get this, and then press your variable button, and then click whatever your variable is, because whatever the variable is, my variable is X because I titled my column X. Remember that? Whatever you title your column is, just put that in, and then click on that one, click on that variable, and then press enter, and you should get a sample standard deviation of 9.67 ish, and then you divide that by the square root of n. So square root, or n is 40. So that is equal to 9.67 divided by square root of 40, which is equal to approximately 1.53. Approximately equal to 1.53. Okay. And now we need to find our y, because we need to find our the mean of our sample. So do the same thing again. Go to like a different white rectangle square. Then basically go to your data, press menu, go to your data, go to list math, and then go to your mean, and then press var again, your var button, and then press whatever your title name is again. Mine is X, and you get like 299 over 4, which is equal to 74.75. So that's your mean of your sample. So you don't want to do other math. If you want to, it's just time wasting. You basically just use your spreadsheet to do this, and you basically just write the number down. And then your t-score, which is just your y. So it's 74.75 minus your 80. Okay. So you want to minus your 80 because it's y minus the mean UO, divided by your standard error, which is 1.53. So using your math, your calculator, 74.75 minus 80 divided by 1.53, which is approximately equal to negative 3.43. And you have to write your degrees of freedom, df, which is just n minus 1. So your n is 40, so 40 minus 1 is 39. So you have a t-score of negative 3.43 with a degree of freedom of 39. Okay. And you always write your alpha level. Your alpha level is 0.05. Unless the question asks for a different one. Usually it's just 0.05. If they don't specify, it's 0.05. And then basically you draw a picture. Yeah, general gist of how this looks. Oops, sorry. It's supposed to be a T model, so a little smaller than that. So it's like a little bit more spread out and more flattened. So it's a T model. So you have your mean of 80. So 80 is right here. You have a y of 74.75 here. So 74.75. And you have a standard error of 1.53. Right? So basically, what is the so basically we're gonna say if it's like if this has a chance of like getting a 80 or above. So what's the probability that he will like fail the class? Because we want to ask like, even though you could like write what's the probability that oh sorry, about the null hypothesis, it was actually HO is equal to U, sorry, U of A is equal to 80, and U is less than 80. sorry, it's less than 80. Because it's basically kind of like the same question. Because it's asking HA basically is what's the probability that if it's greater than 80, what's the probability that he'll pass the class, and less than 80 is the probability that he'll fail the class. So whatever the probability is that he'll fail the class, it would just say like if you fail the class and he has a pretty high probability on that, then basically you could just say that he doesn't have a really good probability of passing the class. So you could just do something like that. So let's just say it's less than it. Because since it's negative, we could just go with this area. Okay. So using this area, we could basically say we just need to look for the smaller area and say what's the probability that he will basically fail the class. So looking at our mechanics, basically what you're gonna do is that basically you're gonna go to your calculator. So press on to go back to your menu. Go to A calculate, and then press menu. You could go to probability or statistics, doesn't matter. Just go down to distributions, the one that says distributions, and click TCDF, the one with the C, not the P. And then your lower bound is negative E999 because you gotta think about it because this guy get really negative, so it's like negative E99, a really big negative. And then upper bound, which is your 74.75, right? But you actually have to write the t-score for this one. Z-scores, you only write the value. For t-scores, you write for t-models, you have to write the t-score. So your one is negative 4.3, a negative 3.43, with the degrees of freedom of 39, basically. Okay. So the probability, your p-value, is equal to 0.007. Oops, sorry, there's a one more 0.072. So this is the probability that he'll basically kind of like pass the class. Because if this is the probability that he's not gonna make it in the class, then this is the probability basically he's gonna fail, right? So that's the probability that he won't like make it. Because you can also think about it with the standard error. Because if you have a 1.53 and you have something as small as 3 standard deviations, if it's two standard deviations, it might be understandable, but 3 standard deviations is really small, so it's really unusual. So he might not pass basically. So he has a 1.53 right here. So basically, if he has a pretty good chance if it's just 1 standard deviation away, so it's like a 79 or 78, but it's at 74, so it's really low. So he might have a really small chance of doing a getting passing. So that's your p-value. So logically, you just have to think about it. So you have a 0.0072. Okay. So now you can write your conclusion. So conclusion based on my based on not my on the p-value of 0.00072, which is less than the alpha level of 0.05, I reject the null hypothesis. So you're basically saying that he's not gonna get 80 because like we said our null hypothesis was h or with u is our null hypothesis is the mean is equal to 80, and I changed it in the middle. I'm sorry about that. Which your mean is less than 80 now. So you say the alternative hypothesis might be true. So there is evidence to suggest the alternative hypothesis is true. I'm just gonna write equal to true. You have to write this in context. So what I'll write is that based on my p-value of 0.00072, which is less than the alpha level of 0.05, I reject the null hypothesis that that the student will score will pass the class. Basically, will pass the class. There's evidence to suggest the alternative hypothesis that the student would fail the class is true. So basically, write that in context. So that's basically all you had to do. If and then you can follow this up with a confidence interval. So let's say you want to do a 95% confidence interval, which is usually the confidence you want to do. Your mean is your y, so you're 74.75, and your standard error was basically the same thing. It's just your standard deviation, which is 9 point just to make sure I'm not wrong, 9.67, I believe. Yes, 9.67 divided by square root 40, which was 0.67 divided by square root 40, which is 1.53 approximately. And then basically you need to get the t-score now with a right degrees of freedom. So go to your calculator, press menu, go to your probability or statistics, doesn't matter. Go to distribution again, go down to distribution, go to inverse t, so number 6. And then your area is whatever area you want to think it is. So if you have a 95 like area, right? Since I set the as same with the z-score, it does something like this, right? And it calculates the area all the way up here, like when you want it right here. But instead you want the area to be like right here, you know, in the middle, not including this section. You gotta have to do that. You have to just do math. Since the T model is basically symmetric also, so you want a 95% area, right? So between is 95. So let's draw this out. So if this area is 95, it's symmetric on both sides. That means this is 2.5% and this is also 2.5%, right? Because like 2.5 is symmetrical to both sides, so they're equal to each other. And then 2.5 plus 2.5 is 5, plus the 95 is 100, right? So your entire area right here is 97.5, because 2.5 plus 95, so it's 97.5. But write that as a decimal, so it's 0.975. And your degrees of freedom is 39, basically. So because it was n minus degrees of freedom of 39, because it's n minus 1 and your n was 40, so n minus 1, 39. So okay, and you get a let me delete the pictures because we don't need this anymore. We have a degrees of freedom of 39, right? And your inverse t for that area using your calculator is approximately equal to like 2.02. So you're basically doing the math is basically just your mean, so 74.75 plus or minus your t-score of degree at 39, so it's just 2.02 times your standard error, which is 1.53. So 2.02 times 1.53, 74.75 plus that number, or 74.75 minus that number, and you get like somewhere in between 71.66 and 77.84. See how like 80 is not in this and 80 is like outside above it? Since 80 is not in this range and you're 95%, basically the confidence interval for a T model could also tell you if you're likely to pass the class in this situation, if you're likely to pass the class. But since 80 is not in here and you need 80 above to pass, that means you're likely to fail, right? So basically, how you write this in words to explain your confidence interval is that I'm 95 in this scenario. I'm 95% confident that the true mean value of my test score is within the interval 71.66 to 77.84. So you could explain, and you just have to basically write that. This you were calculating the score. You have to find out what these numbers basically stand for. This it stands for like the range of numbers in which where your test score might fall under if you take like basically more tests. So If you don't want to do the math, always you could basically use your calculator. So go back to your calculator, go to menu, go to statistics, which is number 6, then go back down to number 7, which is stats test, and then you press the t-test, which is your one sample t-test. And then it says data input method, put stats, because you got to put in the numbers. You could put in the data if you want, but usually if you calculate all the stats, you'll be fine. Your UO, as I said, was your 80, because you need 80 above to pass. Your X with your X is basically just your Y, so it's gonna be your mean of your sample. So it's gonna be 74.75. SX is your standard deviation, so just put your standard deviation, which is 9.67. And your N was your sample size, so it's 40. And you wanted to see if it's smaller than it. So HA is U is less than UO. So you want to see the probability that you fail. And you press OK. And it basically gets you the same numbers. But since you round it, basically, the numbers are going to be off just a little bit, but it's not going to make that much of a huge difference. So your T, using your calculator, you get your T score is negative 3.43, which is true because that's what we got. But the decimals might be a little off if we started like writing a bunch of the decimals. Our p-value is 0.00071 instead of when we wrote 0.00072 because we did like some kind of rounding sometimes, but it's not gonna be that much of a difference. It was just a difference of 0.00001 basically. It's not that much of a difference. The degrees of freedom is 39, and your x is which was your y is 74.75, the mean of your sample, and your standard deviation was 9.67, was what you had your standard deviation based off your sample, and n was your sample size, which was 40. So you can basically do this if you don't want to do all the math. So you get your p-value, which is 0.00071, which is less than 5. So you had to basically, you reject the null hypothesis because it's way too unusual. So it's not because it's too unusual for it to be away from 80. So basically, it's saying that your 74.75 would be really difficult for you to get to 80 or above. So it's too like unusual for it to be to get any higher. And then if you want to do a confidence interval, go to menu, go to statistics again, number 6, go to confidence interval number 6, and then go to a t interval basically. So your second one. Input method stats, okay. And then your x is your 74.75, the mean of your sample, right? Your standard deviation, 9.67, rounded-ish. It's probably a little bit more precise. If you want to put the operation, like you put like, you want to calculate the actual like variance, which is just the standard deviation squared, and then you square root it. Like you actually put the square root symbol, and then divide by square root 40, to get the standard error. I mean standard deviation, which I mean just write the variance and then put a square root over the variance if you want to be precise as possible. Your n is 40, but rounding is not that much of a difference, so it should be fine. And your C level is 0.95. This one's actually right. You don't have to put 0.975 and do the math to see if it's to get the symmetric number, and then you add it to get like the 9.75. I mean 0.975, because this one would actually give you the one in between instead of the one from like the left all the way up to that number. So you have that number, and you basically get your confidence interval, which is 70. The lower is 71.66, as I said, and the upper, well rounded, and the upper is 77.84. There's a bunch of decimals, so if you want to write those two, if you want to be more precise, it's fine too. And then you have your mean, your margin of error, which is 3.9, which is basically just your your t score, which is basically your t score times your standard error. So that's basically what it is. And then you have degrees of freedom, which is 39, and then you have your standard deviation was 9.67, and your n, which is 40. So you don't want to do any of the math for the confidence interval, and you want to just get this. You could do this. So if you ever want to find like like whatever the inverse area for like a 95 is, you basically just do the confidence interval, go to your margin of error, find out what your standard error is, and then divide by that margin error, divide by that standard error to get your your t score for that inverse area. So it just be like, because margin error is just t score times your standard error. So you could just do that. Use your calculator if you're using an Inspire. Well, that basically covers everything for a one sample t-test and its confidence interval. Thanks for watching, and I'll see you at the next math record.